Maybe most they can do is probably just eat. Maybe we try to enjoy.
Okay. Hello. Okay. Okay, well, I'll just start. Yep, no problem. Okay. Well, if you have any questions, yeah. Yeah. Okay. So I mean, my original plan was I wanted to explain how we could, using the properties we've seen so far, we could prove things like strong induction and the well ordering principle. That was my original plan. So unless there's some concept you want to go over, we'll just try and do those things. Okay, sure. So, you know, usually in first year, yeah, no problem. Okay, so normally in first year, these things are stated as like axioms. You know, you have induction, then you have strong induction, and you have the well ordering principle. And it might be mentioned sometimes that they are like somehow equivalent. Well, whatever that means. But what we're going to do is we're going to, so we've shown that induction holds, and we've shown the property that, you know, any two natural numbers can be compared with each other. And we'll use those two properties to prove that strong induction, we'll prove the strong induction principle and the well ordering principle. Okay. Okay. Let's state strong induction. Okay, so P of X is a property. So it's just something we want to prove for all the natural numbers. Okay, and then we have a hypothesis, which is we'll assume that for all n, if for all k less than n, P of k, okay, so then P of n, okay, so this is our assumption. Our assumption is that for all the natural numbers n, if P of k holds for all k less than n, then P of n holds. And then as a result, if we assume that, our conclusion is that P of n for all n. Okay, that's our theorem. Oh, someone else came. Okay, so let's just try. First, we want to just like kind of unravel what this says. Like in particular, we want to unravel a little bit what this assumption is. We actually have an assumption for each natural number. So let's just try and write down all our assumptions. Okay. Okay, so let me write down the hypothesis again. For all n, and the hypothesis is for all k less than n, P of k, this statement implies P of n. Okay. That's the assumption. That's what we, if you verify this condition, then you get the conclusion, which is that for all n, P of n. Okay, so this is like the assumption. So when n equals 0, this assumption says if for all k less than 0, P of k, then P of 0. Okay. And it says for n equals 1, it says if for all k less than 1, P of k, then P of 1. And for n equals 2, it says if for all k less than 2, P of k, then P of 2. And it goes on and on like that. Maybe we'll write it for n equals 5. You know, if for all k less than 5, we have P of k, then we can conclude P of 5. Okay. So we'll try and unravel what each one means. First, we'll look at n equals 0. What does this mean? So if we unravel it, there are no natural numbers less than 0. Let's see why. This is just, if we translate this into what we've, our construction, this says that, so less than is really an element of, so this really says k is an element of 0, and 0 is the empty set. Okay. Okay, so this this hypothesis, the statement for all k less than 0 p of k, this is always satisfied because there's no k that are less than 0. Okay, so what this assumption says for n equals 0 is that we have to assume p of 0. So the assumption says that p of 0 holds. Because this statement for all k less than 0 p of k, that is always true. Okay. So when we put n equals 0, this statement just says assume p of 0. When we put n equals 1, what this says is that if we just write down, maybe I'll write down our natural numbers down here. 0 is the empty set. Well, there's nothing in the empty set. 1 is just the set that contains 0. In other words, it's the set containing the empty set. Okay, that means that if I assume that for all k is less than 1, I'm saying that for all elements of 1, p of k. So then what we can say is that if p of 0, then p of 1. Okay, that's what this. Okay, and then this statement says that, well, 2 is just the set 0, 1. So the n equals 2 says that if p of 0 and p of 1, then p of 2. Okay, and then if we continue, someone else gave. We continue the n, when n equals 5, it says if p of 0, p of 1, p of 2, p of 3, and p of 4, then p of 5. Okay. Okay. And then it goes on and on like that. Okay, so that's what the different assumptions mean. Okay, so when you're applying strong induction, one way you might do so is first by checking p of 0, then checking that p of 0 implies p of 1, then checking that p of 0 and p of 1 implies p of 2, and on and on. Okay. And then once you check all of those conditions, you're allowed to conclude that p of n holds for all n. Okay, before we proceed with the proof of strong induction, you guys know, does it make sense why we call it strong induction? Okay, please tell me why. Yeah, right. So when you do the inductive hypothesis, You get to assume something stronger. That means like what you have to do is like easier. You know, so somehow like regular induction says that you have to show that P of 4 implies P of 5, and somehow assuming P of 0 up to P of 4 makes proving P of 5 easier. Okay, yeah. You know, so as a tool, it seems like it's a stronger tool, but we see that we only need regular induction to prove strong induction. So it's kind of, it's not actually stronger, you know. Because any question that you can answer with strong induction, you can just answer it. You can just do the same thing with regular induction. That's what this proof tells us. So let's just prove this, and we'll take a quick break. Okay. So proof. So P of n is a statement, and assume for all n the statement that k is less than n, P of k implies P of n. Okay. And now we want to kind of make up a inductive hypothesis or something. Okay, so let's just make up a new letter. Let Q of n be the statement k is less than n. Let's see, how should I write it? I should write it like for all k is less than or equal to n, P of k. That's Q of n. Okay. And we're going to prove Q of n by induction. And the trick with this is like we have to do some tricks with less than or equal to. Okay, so now we're going to prove Q of n by just regular induction. Notice that if we prove Q of n for all n, as a corollary, we've proved P of n for all n. So let's just notice Q of n for all n implies P of n for all n. Okay, we're going to prove Q of n by induction. To prove Q of n by induction, we need to show that Q of 0 holds. Q of 0 is the statement that for all k less than or equal to 0, P of k. In other words, this is just the statement P of 0, but k less than 0, P of k implies P of 0. That's our assumption. Okay, and this is satisfied, so P of 0. So P of 0 and then P of 0 is the same as Q of 0. Okay, so Q of 0 holds. Okay, so we've got the base case. it's just kind of, oh, sorry, before I move on, there's a question which says, is it just more base cases in strong induction? What I will just say that so this is a common like thing that will happen in strong induction proofs, that you have to do more base cases. So I will just say that it depends on the type of question that you use strong induction for. Because, you know, sometimes you just have the same, just one base case, and sometimes you can have more. It just depends on like what problem you're working on. Okay. Yeah, I'll just say it just depends. Okay. Okay, now we want to keep on going and we want to prove. So we want to apply induction. That means we need to assume Q of K for some natural number K. And what does that mean? So we assume that P of K for all K less than or equal to N. And we want to show Q of K plus, or we want to show Q of N plus 1. Okay. First, we want to show P of N plus 1. Okay. So how do we do that? Well, here's our strategy. We have P of K for all K less than or equal to N. So we want to prove that this means P of K for all K less than N plus 1. Now, our assumption will tell us, like, one of our hypotheses is that if P of K for all K is less than N plus 1, then P of N plus 1. Okay, so if we show this thing, we get P of N plus 1. And then we want to show that if we have P of K for all K less than N plus 1 and P of N, then we really have P of K for all K less than or equal to N plus 1. Once we get that, that's just Q of N plus 1. Okay. So that's our plan. And so we want to show this. We want to show P of K for all K less than N plus 1. So let K be less than N plus 1. Well, what is N plus 1? N plus 1 is just N union singleton of N . Okay, so if K is less than N plus 1, either K is in N or K is in N. In other words, either K is less than N or K is equal to N. And in other words, this is just another phrase for K is less than or equal to N. Okay, But our assumption, our hypothesis, our inductive hypothesis is that P of k is true for all k less than or equal to n. So we can say then P of k. Okay, so we've shown for all k less than n plus 1, P of k. So we've shown this. Okay. And now our assumption is that if P of k for all k less than n plus 1, we get to conclude P of n plus 1. And now we have P of n plus 1, and we have P of k for all k less than n plus 1. So we have, so for all k less than or equal to n plus 1, P of k, and that's just Q of k, Q of n plus 1. So Q of n plus 1. And what we've shown is that Q of n implies Q of n plus 1 for all n. Okay, so now by induction, Q of n for all n. Okay. So if we rewrite this, what it means is that we've shown that for all n, for all k less than or equal to n, P of k. So it seems like on the surface, this seems like a lot stronger than just for all n, P of n. But if you think about it, this is really the same as just proving for all n, P of n. You know, because first we prove P of 0, then we prove P of 0 and P of 1, then we prove P of 0, P of 1, and P of 2. And so we're just restating P of 0, P of 1 many, many times, you know. Okay, so that is the end. Okay, so we've proved strong induction. So it's not really strong. It's not really stronger. But it is more just like kind of an organizational tool. It is another way to organize induction proofs. That is why it gets a special name, that's all. Okay. So let us just take a very quick, just a 2-minute break, just long enough for me to restart, and then we'll also talk about the well ordering principle. Okay.